Dragon blazing across the sky 10 times faster than a supersonic bullet. That's how Elon Musk described the dramatic re-entry of SpaceX's Crew Dragon capsule from the Crew 11 mission. And for a moment, it really did look unreal. A fiery streak over San Francisco on January 15th, after undocking from the ISS. It's so amazing. But here's the part that usually gets lost once the clip goes viral. Speed alone doesn't tell you very much. In fact, NASA has flown spacecraft that came back to Earth significantly faster than Dragon ever does. So this isn't a story about headline numbers or who holds the speed record. It's about what those numbers actually mean, and why, in real-world spaceflight, the most impressive part of Dragon's return has very little to do with how fast it's moving. When Elon Musk talks about Dragon crossing the sky at more than 10 times the speed of a supersonic bullet, he's referring to the capsule's velocity at atmospheric interface, roughly 7.8 kilometers per second. That number sounds extreme, but it's also familiar. It's essentially the same speed flown by every spacecraft returning from low Earth orbit, including the Space Shuttle, which typically re-entered at about 7.8 kilometers per second as well. Orion, by contrast, came back much faster. During Artemis 1 in 2022, NASA measured peak entry speeds between 11.0 and 11.5 kilometers per second as the spacecraft returned from lunar distance. Apollo missions experienced similar velocities for the same reason. Leaving Earth's gravity well and returning from the Moon adds substantial orbital energy that must be dissipated during re-entry. The Space Shuttle even flirted with this boundary from the opposite direction. In 1990, during STS-31, the mission that deployed the Hubble Space Telescope, the orbiter reached approximately 7.96 kilometers per second on re-entry, the fastest of the shuttle program. That mission placed Hubble into the highest orbit ever achieved by a shuttle, and the higher the orbit, the more energy the vehicle carries when it comes home. Re-entry speed, in other words, is a function of where you've been, not how advanced your spacecraft is. This raises a fair question. Does faster re-entry mean a better spacecraft? In practice, re-entry velocity is a measure of mission profile, not engineering superiority. What matters is how much energy the vehicle must shed once it touches the atmosphere. Low Earth orbit requires a circular speed of about 7.8 kilometers per second. Lunar trajectories add roughly 2 to 3 kilometers per second of excess velocity, resulting in peak speeds around 40% higher. That additional energy translates directly into more intense plasma formation and heat flux, often an order of magnitude higher than orbital returns. Higher speed does not mean higher performance, it means higher stress. Lunar re-entries generate 10 times the heat flux, risking shield ablation and G-forces. To survive, Apollo and Orion use skip profiles over the Pacific for braking. It's like dipping shallow into thin upper air, like skipping a stone on water to brake a bit and bounce back out to cool off before repeating and finally plunging in. This helps spread deadly heat and G-forces over 30 minutes instead of instant burnout, while aiming for rescue ships nearby. Even so, the super-hot friction vaporizes outer heat shield layers to carry away heat, requiring costly factory rebuilds that slow reuse. Dragon skips none. It endures a simpler low-orbit fireball drop with milder stress, quick parachute splashdown, and fast reflights. However, having a simpler low-Earth orbit re-entry doesn't make Dragon less impressive than NASA's lunar spacecraft. It actually highlights a form of engineering that many NASA veterans once described as impossible. Crew Dragon is the first American crewed spacecraft whose design center of gravity is operational tempo. From the earliest architecture reviews, SpaceX treated flight rate as a hard requirement rather than a long-term aspiration. Since the Demo 2 mission in May 2020, Dragon had shifted from a certification milestone into permanent infrastructure for U.S. human spaceflight. Capsules such as Endeavour completed 6 crewed missions, while Endurance and Freedom flew 4. All of them carried astronauts to and from the International Space Station across a span of years. That record alone would have been considered extraordinary in previous NASA programs. What matters more, however, is the spacing between those flights. Dragon's turnaround is measured in months. In historical terms, that cadence borders on unprecedented. The same pressure vessel, avionics stack, propulsion system, and primary structure are reused with targeted inspections rather than full disassembly. NASA certifies every refurbishment step, but the process itself is streamlined because Dragon was designed to tolerate reuse from the beginning. Nothing about this system assumes rarity. Dragon returns from an orbit roughly 400 kilometers above Earth at approximately 7.7 to 7.8 kilometers per second. Compared to lunar return velocities, that is modest. But frequency reshapes the engineering problem. A spacecraft that flies once can afford mass penalties, bespoke labor, and conservative margins everywhere. A spacecraft that flies repeatedly cannot. Weak assumptions surface quickly. Costs compound. Minor inefficiencies become structural liabilities. Dragon survives that reality because its architecture assumes repetition. Automation replaces manual intervention. Recovery is simplified. And most importantly, thermal protection is treated as a consumable component within a reusable system. That mindset, not raw speed, is Dragon's true breakthrough. Anyway, if you're enjoying this kind of deep, no-hype breakdown of spaceflight, give the video a like. It really helps. And if you want more analysis like this, feel free to subscribe and share your thoughts in the comments. Apollo's command module was optimized for singular achievement. Each capsule flew once and was never intended to return to service. The program's constraints were geopolitical urgency and mission assurance, not sustainability. In that context, expendability was not a flaw. It was an efficient choice. Orion, despite being separated from Apollo by decades of materials science and computational tools, inherits a similar philosophy. It is designed for deep space missions with Earth return velocities exceeding 11 kilometers per second. Those conditions impose extreme thermal loads, and Orion is built with thick margins to absorb them. NASA currently states a target of up to 10 flights per Orion capsule, but those flights are expected to be separated by long intervals. Artemis 1 illustrated why. Orion's Avcoat heat shield protected the vehicle as intended, yet post-flight analysis revealed uneven erosion and cracking patterns that required extensive investigation. None of this compromised crew safety, but it underscored the cost of designing for rare, extreme environments. Orion prioritizes durability over cadence. That choice is rational for lunar exploration, where missions are infrequent and the stakes are maximal. Dragon occupies the opposite end of the spectrum. It does not attempt to span all mission profiles. It focuses narrowly on orbital crew transport and optimizes relentlessly for that role. The Space Shuttle demonstrated that reusability in human spaceflight was possible, but also how it could fail operationally. Each orbiter flew dozens of times, with Discovery reaching 39 missions. On paper, the shuttle appeared to deliver on its promise. In reality, the thermal protection system became its Achilles heel. The shuttle relied on thousands of reusable silica tiles, combined with reinforced carbon-carbon panels on leading edges. These components were theoretically reusable, but practically fragile. After every mission, technicians inspected each tile individually. Minor damage could ground an orbiter for months. Turnaround times stretched far beyond original projections, and per-flight costs ballooned into the billions. The system accumulated what engineers call engineering density, complexity layered on top of complexity, until operational flexibility disappeared. The vulnerability of the tiles to debris impacts was not merely theoretical, as the Columbia accident tragically proved. Dragon's designers deliberately avoided this path. Rather than attempting to preserve the heat shield intact, Dragon treats controlled material loss as normal. It is an acceptance of physics rather than a fight against it. Crew Dragon's heat shield is built from Pika-X, SpaceX's proprietary evolution of NASA's phenolic-impregnated carbon ablator. The material consists of a lightweight carbon fiber substrate impregnated with phenolic resin, engineered to manage extreme heat through ablation rather than insulation alone. During reentry, the outer surface chars and pyrolyzes, chemically breaking down and carrying heat away as material vaporizes. On a typical low Earth orbit return, only about 1 to 2 centimeters of material ablate from tiles roughly 8 centimeters thick. The remaining structure stays intact, keeping the capsule's interior near room temperature. This approach is grounded in proven heritage. NASA's original Pika protected the Stardust capsule during its 12.9 km/s Earth return in 2006, the fastest re-entry survived by any spacecraft at the time. SpaceX's Pika X and later Pika 3 variants refined that concept for consistency, manufacturability, and robustness. Although Dragon is certified for its 7.8 km/s operational envelope, the material itself is capable of far more. SpaceX has stated that upgraded Pika formulations are designed to tolerate lunar return velocities in the 11 to 12 km/s range, driven by Starship's future lunar and Mars missions. In Dragon's case, that capability represents a margin rather than a requirement. Reusability here does not mean preserving material, it means preserving the vehicle. Orion's Avcoat heat shield reflects a fundamentally different set of priorities. It is also ablative, but constructed using a honeycomb structure filled manually with ablative material, then cured and machined. The process is labor-intensive and expensive, but it yields high confidence for rare, high-energy lunar returns. The trade-off is scalability. Avcoat shields are difficult to produce quickly and are not designed for frequent replacement. Orion's heat shield is effectively single-use, followed by extensive inspection and analysis. The shuttle attempted reusability at the material level. Dragon pursues reusability at the system level. Dragon's heat shield is replaced for each crewed mission, but replacement is fast and economical. Some cargo Dragon missions have reused tiles entirely, demonstrating additional margin. This architecture eliminates entire classes of failure modes. Minor surface damage does not automatically imply mission loss. Manufacturing control reinforces the advantage. SpaceX produces Pika X in-house, enabling rapid iteration based on real flight data rather than theoretical assumptions. Since 2021, when NASA awarded SpaceX a $2.9 billion contract to develop Starship as the human landing system, the lunar program appeared to narrow into a single track. SpaceX moved ahead despite legal challenges from Blue Origin, and for a time, Artemis looked less like a competition and more like a schedule built around one company's execution. That balance began to shift as external pressure increased. China's clearly defined lunar ambitions introduced a geopolitical deadline that NASA could no longer treat as abstract. The priority moved from long-term program elegance to near-term national positioning. Speed, readiness, and optionality started to matter more than legacy procurement structure. Out of that environment came a noticeable policy adjustment. NASA began signaling flexibility, less attachment to a single contractor, and more emphasis on demonstrated progress. The agency's language changed first, then its actions. Acting Administrator Sean Duffy reopened the landing discussion, citing delays and openly acknowledging that Artemis 3 would go to whichever system could meet the mission requirements first. That stance was later stated even more plainly under Jared Isaacman's leadership. I don't think it was lost on either vendor that whichever lander was available first to ensure that America achieves its strategic objectives on the moon is the one we were going to go with. The message was not about preference or punishment. It was about the outcome. This reframing puts SpaceX and Blue Origin under equal pressure. The prize is not just contractual. It carries symbolic weight. The distinction of returning humans to the moon for the first time in more than half a century. With that comes scrutiny, expectations, and very little tolerance for missed milestones. From a technical standpoint, SpaceX entered this phase with structural advantages. Starship HLS is not a clean sheet vehicle. It is derived from a system already designed for deep space cargo and crew transport. Engines, tanks, avionics, and manufacturing processes are shared. Reuse of core systems compresses development timelines in ways traditional programs struggle to match. That compression is reinforced by SpaceX's iteration-driven culture. Hardware is built quickly, tested aggressively, and replaced just as fast. Failures are treated as data points, not endpoints. Each version feeds directly into the next. The factory environment reflects that philosophy. It looks more like a mechanical workshop/steel mill than a standard aerospace cleanroom. Yet even with those advantages, the hardest problem remains unsolved. Starship's lunar mission depends on large-scale ship-to-ship refueling in orbit, a process that has never been operationally demonstrated. Until that works reliably, schedule margins remain theoretical. Blue Origin comes from a different engineering tradition. The company has consistently favored a cautious, sequential development model, closer to classical waterfall design, where systems are refined extensively on paper before they are exposed to flight conditions. The objective is to minimize surprises at first launch. That philosophy is reflected in its facilities, which are often described as very modern, clean, and having strict safety procedures. That approach has consequences for the timeline. New Glenn, Blue Origin's first orbital-class rocket, took roughly 12 years to progress from early design work, closely tied to the BE-4 engine program before 2013, to its first orbital flight on January 16, 2025. Over the same period, SpaceX conducted hundreds of Falcon 9 launches, accumulating operational experience in booster recovery, reentry control, engine reuse, and launch cadence. Those flights quietly built the technical foundation that now allows Starship to iterate at a much faster pace. During that gap, Blue Origin focused largely on New Shepard, a suborbital vehicle designed primarily for short-duration human flights. While technically successful, the program contributed little to orbital operations, deep space payload integration, or high-energy mission profiles. The company is not expected to begin flying NASA or commercial scientific payloads until the second New Glenn mission, currently projected for late 2025. That history has shaped skepticism about Blue Origin's readiness to compete at the scale required for sustained lunar operations. That perception has begun to shift. Over the past 2 years, Blue Origin has become more transparent about progress, publishing regular updates and positioning its lunar program as a structured, test-driven campaign rather than a single leap. The company's approach to the Moon is incremental. Fly uncrewed Mark I cargo landers first, then scale to the larger, crew-capable Mark II system later in the decade. The Mark I lander is designed as a self-funded robotic demonstrator, targeting a landing near Shackleton Crater as early as 2026. It means Blue Origin could go to the Moon before SpaceX. This is thanks to Mark I, which does not rely on orbital refueling. It is intended to validate propulsion, avionics, and surface operations in lunar conditions. Data from Mark I feeds directly into the design of Mark II, which is planned to support crewed Artemis 5 missions around 2030, launched via New Glenn with an additional cryogenic upper stage. Recent signs suggest the program is moving from planning to integration. In mid-January, Blue Origin released imagery indicating that Blue Moon Mark I was undergoing final stacking in Florida. The company referenced upcoming acoustic testing, a milestone typically reserved for vehicles that are largely assembled and structurally complete. NASA Administrator Jared Isaacman was shown observing the lander through a facility window, a signal that the project has entered a more visible phase of oversight. A successful Mark I landing would be meaningful, but it would not settle the central challenge of human lunar transport. Carrying people to the Moon requires sustained, large-scale in-orbit refueling. On that front, Blue Origin faces many of the same obstacles as SpaceX. Both systems depend on transferring supercold cryogenic propellants in space while managing boil-off, thermal gradients, automated docking, and precise fluid control in a vacuum. These operations must be repeatable, reliable, and safe at a multi-ton scale. The engineering demands are substantial, regardless of architecture. Blue Origin has indicated plans to demonstrate orbital refueling capabilities between 2026 and 2027 using New Glenn. SpaceX is targeting a similar window, with its first large-scale Starship refueling tests expected around mid-2026. However, those challenges become more demanding for New Glenn. Its upper stage relies on BE-3U hydrogen engines, and liquid hydrogen introduces a different class of complexity than the methane-oxygen systems SpaceX uses. Hydrogen must be stored at roughly 20 Kelvin, making it both extremely cold and exceptionally light. To carry a meaningful amount of energy, tanks have to be larger, insulation more precise, and sealing far more exact. Hydrogen molecules are small enough to slip through microscopic gaps, increasing leak risk during storage and especially during tank-to-tank transfers in orbit. Boil-off is also more aggressive, requiring near-perfect thermal control to keep losses within acceptable margins. On the ground, both companies report encouraging test results, but neither has yet demonstrated large-scale cryogenic transfer in orbit, where vibration, thermal cycling, microgravity fluid behavior, and autonomous control all interact at once. This is where experience matters. SpaceX has accumulated years of flight time beyond Earth's atmosphere, while Blue Origin's limited orbital history remains its most visible constraint. That difference does not decide the outcome on its own, but it shapes the risk envelope. The question is no longer whether either system can work in theory, but which organization can turn theory into routine operation first, and do so with humans on board. Given these constraints, which approach do you think is more likely to deliver a crewed lunar landing first? Let me know how you're weighing the evidence. If you found this breakdown valuable, you can support the channel by liking the video. Subscribe if you want more clear, technical coverage like this, and let me know your take in the comments. The contrast between the two companies is also visible in how they build their launch vehicles. SpaceX chose stainless steel as the primary structural material for Starship. It is inexpensive, forgiving to manufacture, easy to weld, and becomes stronger at cryogenic temperatures. Stainless steel also tolerates high reentry heat, reducing dependence on fragile thermal protection systems and allowing design choices that favor speed of iteration over material optimization. New Glenn follows a more traditional aerospace path. Its structure relies on aluminum-lithium alloys produced through precision machining and friction stir welding paired with a carbon fiber composite fairing. This approach improves mass efficiency but increases production cost, manufacturing complexity, and sensitivity to cryogenic sealing issues, especially when hydrogen is involved. Propulsion choices reflect similar trade-offs. Starship clusters more than 30 Raptor engines on its booster, using a full-flow staged combustion cycle. Historically, this cycle was considered difficult to industrialize, but it delivers high efficiency and scales well in mass production. SpaceX's advantage lies less in any single engine than in its ability to manufacture and iterate them rapidly. New Glenn flies with 7 BE-4 engines on its first stage, using an oxygen-rich staged combustion cycle. The design is simpler and more conservative, trading some efficiency for robustness. On the upper stage, BE-3U hydrogen engines deliver very high specific impulse, which matters for direct injection into high-energy orbits. Reuse philosophy diverges as well. Starship is designed for full and rapid reuse, including second-stage recovery, with the booster intended to be caught by a launch tower. The approach carries high technical risk, but promises minimal turnaround time if it succeeds. New Glenn opts for a more conventional barge landing for its booster, a lower-risk method with higher operational overhead. The upper stage, for now, remains an open question. These choices place New Glenn closer to Falcon Heavy in mission class than to Starship. Its payload capacity is lower, but its Hydrolox upper stage excels at sending moderate masses directly into geostationary transfer orbit or lunar trajectories without refueling. That capability aligns well with Blue Origin's commercial launch ambitions. Starship, by contrast, is built around orbital refueling from the start. Its architecture assumes that propellant transfer becomes routine, because its long-term objective lies beyond Earth orbit entirely. Mars drives the design, even when the near-term mission is the Moon. On Saturday, January 17th, the hardware for Artemis II rolled out to Pad 39B at Kennedy Space Center, a major milestone toward sending humans to the Moon for the first time in more than 50 years. With the Space Launch System, Orion, and the European Service Module now standing tall on the pad, NASA engineers are spending the next several days preparing for what's called the wet dress rehearsal. It's a full simulation of fueling and the countdown process, meant to catch any last-minute issues before launch day. Set to happen no later than February 2nd, the two-day rehearsal will involve loading the rocket with cryogenic propellants, running through a full countdown, then draining the tanks. If anything unexpected comes up, the SLS and Orion can be rolled back to the vehicle assembly building for adjustments. Only when this test goes flawlessly will NASA move toward the final countdown to launch. Everything has to stay on schedule to fit the launch window between February 5th and April 2026. What makes Artemis II especially meaningful is its shift from uncrewed tests to bringing humans back near the Moon. It's the bridge between exploration by machines and exploration by people. The biggest change is clear. Artemis II will be the first crewed flight of the Artemis program, and the first time humans have ventured close to the Moon since 1972. While Artemis I was an uncrewed test flight, Artemis II will carry 4 astronauts. The Orion spacecraft for Artemis II, named Integrity, won't enter lunar orbit. Instead, it will perform a long loop around the Moon before returning to Earth on a 10-day mission. Traveling farther than any spacecraft carrying humans has ever gone, about 7,500 kilometers beyond the Moon's far side. Using the same SLS Block 1 rockets as Artemis I, Artemis II incorporates a range of refinements: improved fueling systems to prevent leaks, upgraded rainbirds for more even water deluge coverage, and stronger mobile launcher components like reinforced blast shields and flame deflectors. Sitting atop the SLS is Orion, this time equipped with systems designed for a human crew. Engineers added vibration dampers and sound insulation to reduce the intense shaking and noise during launch. A major upgrade for Artemis II is its optical laser communication system, which can transmit video at 260 megabits per second from lunar distance, a huge leap from the radio setup used on Artemis I. NASA also addressed issues discovered during Artemis I. The first Orion's heat shield showed unexpected burn patterns and small gaps after re-entry. For Artemis II, engineers reinforced vulnerable spots and adjusted the gaps between tiles to prevent overheating. Instead of removing the entire heat shield for inspection, they'll use cameras and quick scans to save months of time. To further ease the heat shield's workload, NASA modified the spacecraft's skip entry profile, changing its re-entry angle to lower thermal stress by up to 20%. The new plan targets a splashdown off the coast of San Diego, a smoother and safer finish for the crew's return. Technical testing and preparation for Artemis II have taken a more refined, data-driven path than Artemis I. When Artemis I's SLS core stage went through its Green Run series at Stennis Space Center in 2021, NASA conducted a full-duration test firing of all 4 RS-25 engines, the same engines once used on the Space Shuttle. The lessons learned from that test, along with improved production methods, allowed engineers to streamline the process for Artemis II. Instead of repeating the full Green Run, Artemis II's core stage went through a focused series of component evaluations, RS-25 engine checkouts, program-specific engineering tests, and full-stack verifications at Kennedy Space Center. This approach reduced risk while keeping the mission timeline for the first crewed flight on track. One key improvement for Artemis II is direct access to the flight termination system from the launch pad. During Artemis I, if issues arose in that system, NASA would have had to roll the rocket back to the vehicle assembly building since the mobile launcher didn't allow pad access. The updated design for Artemis II fixes that, improving flexibility and turnaround efficiency. The mobile launcher itself has also seen major upgrades. After Artemis 1, the structure sustained heavy wear from the rocket's acoustic shock and engine exhaust. For Artemis 2, NASA repaired and reinforced the tower, strengthening blast protection and integrating a slide wire escape system. This safety measure gives astronauts a rapid way to evacuate in the unlikely event of a pad emergency. To ensure every system performs flawlessly, NASA turned to advanced supercomputers that simulate the rocket's behavior under extreme conditions. The SLS flight software, essentially the rocket's brain, monitors thousands of data points, manages the engines, and can initiate emergency procedures within milliseconds if necessary. Most of NASA's mission-critical flight code is written in C and C++, languages known for their precision and reliability in safety-critical environments. For ground-based simulations and testing tools, engineers use more flexible programming languages like Python, Java, JavaScript, and MATLAB, which can auto-generate sections of control code for modeling and validation. While Artemis 1 validated the full integration of SLS and Orion, Artemis 2 represents the bridge toward Artemis 3, the mission that aims to land astronauts on the Moon once again. Achieving that goal will depend on another emerging capability: in-orbit refueling. This system, designed to transfer methane and oxygen to the human landing system through a series of tanker dockings, will be key to enabling sustained lunar missions without relying on enormous single-use launch vehicles. Looking further ahead, the technology of in-orbit refueling could reshape how humanity builds a permanent presence on the Moon. This capability would not just extend NASA's Artemis missions, but also make private ventures, like Elon Musk's proposed Alpha Moon base, far more achievable and efficient. SpaceX has identified Shackleton Crater near the Moon's south pole as the preferred location for Lunar Base Alpha. The area offers near-continuous sunlight, ideal for solar power, and is believed to hold significant water ice deposits in permanently shadowed regions. Operations would begin with uncrewed preparation missions in 2026. More than 20 empty starships would land permanently at Shackleton Crater, serving as the first habitats. Each 50-meter-tall, 9-meter-wide ship would be modified by autonomous robots, main tanks, converted into living areas, around 1,400 cubic meters each, roughly the volume of 30 school buses. Payload bays, outfitted as labs, greenhouses, or workshops. Engines, retained as built-in backup power and heat sources. The design eliminates traditional base construction. Each ship becomes part of the settlement, connected by airtight passageways like modular blocks. Within the first day, robots would deploy solar panels, melt ice, and begin producing power and fuel. Each ship would unfold about 200 square meters of solar arrays, generating up to 100 kilowatts of electricity. Mining units would extract and process ice into water, oxygen, and methane through electrolysis and chemical conversion. 3D printers would then use lunar soil to create roads, radiation shielding, and antennas. Finally, automated systems would test life support functions, air recycling, CO2 scrubbing, and temperature regulation, laying the groundwork for the first human crews to arrive. Step 2. From 2026 to 2027. Master refueling and build the ice factory. In 2026 and 2027, SpaceX takes the critical step of mastering in-orbit refueling. Once fully fueled, each lander begins an 8-day journey to Shackleton Crater at the Moon's south pole. After touchdown, robotic ramps deploy small 4-legged mining robots designed to operate in the deep, cold shadows of the crater. These machines use radar to locate ice buried under lunar soil, drill into deposits as cold as -230 degrees Celsius, and melt them with heaters and microwaves to collect liquid water. That water becomes the foundation of a self-sustaining energy system. Electrolysis splits the water into hydrogen and oxygen, while Sabatier reactors combine the hydrogen with carbon dioxide from lunar regolith to produce methane fuel and additional water. Every ton of ice can yield about 0.7 tons of liquid oxygen and methane, and Shackleton is believed to contain billions of tons of ice reserves. Within the first few weeks, Solar-powered processing units operate continuously, connecting mining robots to Starship tanks through insulated pipelines. By the third week, the first lunar-made fuel is produced, a major milestone that removes the need to ship propellant from Earth. This lunar refueling capability allows the next 50 starships to operate independently and doubles as a full-scale test bed for Mars logistics. Step 3. 2027. Cargo City grows. By 2027. Weekly cargo starships begin landing 100 tons of supplies and equipment each at Shackleton Crater. These missions bring greenhouses for growing fresh produce, 3D printers that turn lunar dust into usable tools, small hospitals for medical support, and road-building machines to link the growing settlement. Autonomous systems connect over 50 landed starships to form a larger network nicknamed Auda City. By cutting passages between tanks, they create shared corridors, airlocks, and multi-level living spaces. Step 4. 2028. First crew arrives. In 2028, the first crewed starships finally touch down at Alpha Moon Base, carrying between 10 and 20 astronauts. Crews will cultivate vegetables in hydroponic farms, oversee the ice mining and refueling systems, and continue expanding the interconnected city. By 2029, dozens of people could be living on the Moon full-time. What began as a research outpost evolves into a functioning settlement that tests the full suite of technologies needed for Mars: self-sufficient life support systems, radiation-hardened habitats, and medical care designed for reduced gravity. The first concern centers on hardware. NASA's moon base depends entirely on SpaceX's Starship system. The vehicle must land on the lunar surface, deliver cargo, and return. The technical requirements are substantial. Starship needs reliable booster recovery and reuse. It requires orbital refueling, which demands as many as 20 refueling flights per mission. Long-duration cryogenic propellant storage in orbit remains undemonstrated. The lunar landing and takeoff systems exist only in testing. Artemis 3 has slipped repeatedly from 2025 to 2026 to 2027. Current realistic estimates place it in 2028 or later. If NASA cannot land astronauts on schedule, building an entire base appears unrealistic. The community's skepticism is grounded. You cannot construct lunar infrastructure without a transportation system to deliver it. This is where Isaacman's experience becomes relevant. He flew on Inspiration 4, the first all-civilian orbital mission. He commanded Polaris Dawn, which tested SpaceX's extravehicular activity suit and reached higher altitudes than any crewed mission since Apollo. More importantly, he observed SpaceX's operational model firsthand: iterative testing, rapid failure analysis, quick design changes, and continuous improvement. Previous NASA administrators viewed delays as problems requiring investigation and review boards. Isaacman understands them as part of the development process. He has seen SpaceX fail, publicly learn quickly, and succeed on subsequent attempts. As administrator, he can align NASA's expectations with SpaceX's actual development pace. Instead of imposing political deadlines that inevitably slip and damage credibility, he can establish schedules based on hardware maturity. He can push NASA to accept test-to-failure philosophies rather than demanding perfection before flight. Additionally, Isaacman has direct relationships with Elon Musk and Gwynne Shotwell. That eliminates bureaucratic communication layers. When technical issues arise, he can coordinate solutions faster than administrators who operate through formal channels and contractor management structures. The second concern is financial. NASA operates on a budget of approximately $25 billion annually. That funds everything. Recent proposals suggest NASA faces potential cuts, not increases. The fiscal year 2026 budget includes a proposed 24% reduction. While Congress will likely modify that figure, the political environment does not favor massive new spending. Building a permanent moon base is expensive. Conservative estimates range from $100 billion to $200 billion over 15 to 20 years. That represents 5 to 10 billion annually on top of existing Artemis costs. The ISS cost roughly 150 billion over 3 decades. A lunar base would be comparable or higher due to distance and environmental challenges. The community's concern is valid. Where does that funding come from? NASA cannot print its own budget. Congress controls appropriations, and Congress has repeatedly demonstrated more interest in distributing contracts across districts than in funding ambitious exploration goals. Isaacman brings a different perspective to this problem. First, he understands cost efficiency from building shift payments into a multi-billion-dollar company. He has personally funded space missions inspiration for what reportedly cost under $200 million, dramatically less than equivalent government programs. Second, Artemis has something many NASA programs lack: bipartisan political support. The program began under President Trump in 2017, received funding increases under President Biden, and was reaffirmed by Trump's December 2025 executive order establishing a 2028 lunar landing goal. Both parties have invested political capital. Third, national security concerns now drive space policy. China is developing its International Lunar Research Station, with Russia and other partners targeting the 2030s for operational capability. The United States historically increases infrastructure investment when rivals highlight strategic vulnerabilities. Current examples include data centers, semiconductor facilities, and energy infrastructure. Isaacman can frame the moon base in terms Congress understands: strategic competition and economic security. As both a businessman and astronaut, he has credibility that career bureaucrats lack. Additionally, he can restructure NASA's approach to leverage commercial partnerships. Rather than NASA designing and building everything, the agency can become a customer for commercially provided services. SpaceX develops Starship with significant internal investment. Other companies: Blue Origin, Axiom Space, Sierra Space could provide modules, habitats, and systems under performance-based contracts. The budget problem is not solved, but Isaacman's background provides better tools to address it than previous administrators possessed. The third concern is NASA's operational tempo. The SLS began development in 2011. Its first flight occurred in 2022, 11 years later. Development costs exceeded initial estimates by billions. Each launch costs approximately $4 billion when including program amortization. Compare that to commercial space. Falcon 9 went from concept to first flight in 6 years. Starship progressed from announcement to orbital test flights in roughly 5 years. When SpaceX encounters problems, fixes happen in weeks or months. When NASA encounters problems, review boards convene for years. This is not because NASA engineers lack competence. The agency operates under different constraints. Every decision involves multiple approval layers. Contractors are distributed across all 50 states for political reasons. Risk aversion became institutionalized after the Challenger and Columbia tragedies. The result is a predictable pattern. Administrations announce bold goals. NASA begins development. Timelines slip. Costs increase. Programs stretch across decades. President Bush announced lunar and Mars goals in 2004. 20 years later, the United States has not returned to the moon. Even with Starship operational and budget secured, NASA's institutional structure could slow lunar base construction to an unacceptable pace. This represents Isaacman's most difficult challenge. He has operated in the private sector his entire career. He has experienced how SpaceX moves from decision to hardware in months. He knows the difference between commercial timelines and government timelines. As administrator, he has the authority to change how NASA operates. He can streamline decision-making processes. He can reduce approval layers for non-safety critical decisions. He can empower program managers to move faster. More fundamentally, he can shift NASA toward becoming a customer rather than a manufacturer. Let commercial providers design and build components. Let NASA focus on requirements, safety oversight, and mission integration. Use performance-based contracts that incentivize speed rather than cost-plus contracts that incentivize slow progress. The challenge is real. Changing institutional culture requires overcoming entrenched interests. Contractors benefit from existing arrangements. Congressional members protect jobs in their districts. Career officials resist rapid change. Whether Isaac Mann has the political capital to drive that transformation remains uncertain, but he has better preparation for the attempt than any previous administrator. Isaac Mann's approach aligns with Elon Musk's plan to center on Starship. Elon Musk has stated this directly: Starship will enable a permanent base on the Moon. The concept is straightforward. Rather than launching separate habitat modules, use Starship's structure. The vehicle's upper stage provides approximately 1,000 cubic meters of pressurized volume, equivalent to the entire ISS's habitable space. After landing, SpaceX can convert fuel tanks into an additional living area, adding roughly 1,400 cubic meters. That totals 2,400 cubic meters more than double the ISS, delivered in a single launch. The conversion process involves removing propulsion systems and installing interior structures. Engineers would add a floor running through the center of the hull, dividing the space into levels. Life support systems, air recycling, water recovery, temperature control would be integrated throughout. The result would be living quarters, laboratories, storage, and operational spaces. This approach eliminates the need for Gateway, the planned lunar orbital station. Starship can travel directly to the lunar surface with crew and cargo. That saves time, money, and complexity. It also means NASA can focus resources on surface operations rather than orbital infrastructure. Power generation remains a challenge. NASA has contracted with 3 companies to design a fission reactor delivering at least 100 kilowatts. That provides steady power during the 14-day lunar night when solar panels are useless. The reactor would support habitats, rovers, and resource extraction operations. As Starship Flight 12 draws closer, Starbase has entered one of its familiar high-pressure phases. Hardware moves quickly between the production site and Massey. Crews work through the night. Timelines compress. In the middle of that activity, SpaceX revealed something that immediately drew attention across the aerospace community. An upgraded Raptor 3 engine, finished in a striking blue-black coating, signaling that the propulsion system beneath Starship is undergoing a deeper transformation than previously understood. This version of the engine is scheduled to debut aboard Starship version 3, with its first flight targeted for the first quarter of 2026, coinciding directly with Flight 12. The reveal was brief and understated, typical of SpaceX's approach at this stage, yet the implications were unmistakable. The engine looked different in a way that went beyond refinement. It carried the visual confidence of a system that has moved past experimentation and into deliberate industrial form. Earlier, Raptor engines always conveyed effort. Raptor 1, the original flight-capable version, delivered roughly 185 metric tons of thrust with a specific impulse near 350 seconds. Its dry mass hovered around 2,080 kilograms, and once vehicle-side commodities and hardware were included, the installed mass reached approximately 3,630 kilograms per engine. Visually, it resembled a densely packed industrial machine, crowded with pipes, cables, covers, and exposed metal surfaces that evoked heavy manufacturing equipment from decades past. It worked, but it looked like something that had been repaired repeatedly, adapted, and readapted to survive each new test. Raptor 2 represented a meaningful step forward. Thrust increased to about 230 metric tons, while specific impulse settled slightly lower, around 347 seconds. Engine mass dropped to roughly 1,630 kilograms, and installed mass decreased to about 2,875 kilograms. The engine appeared cleaner and more organized, though still surrounded by visible plumbing and heat protection blankets. Many observers compared it to a well-built gaming computer, powerful and functional, with its internal cables still visible through the case. Raptor 2 brought reliability and manufacturability closer to SpaceX's goals, yet it remained an engine in transition. Raptor 3 completes that transition. At first glance, the engine looks almost unreal. The exterior is smooth, dark, and sculptural, with almost no visible pipes and no external heat shield blankets. Bolts and protrusions have largely disappeared. The surface appears continuous, minimalistic, and deliberate, leading many to describe it as resembling an alien artifact or a piece of industrial art. When side-by-side images of Raptor 1 and Raptor 3 circulated, the reaction was consistent. The earlier engine looked like an industrial factory machine from the 1990s. The new one looked like something designed for a science fiction film set decades in the future. That appearance reflects concrete engineering changes. Raptor 3 produces approximately 280 metric tons of thrust at sea level, with a clear development path toward exceeding 330 metric tons in future iterations. 330 metric tons is almost double the thrust of Raptor 1. A single Raptor 3 produces more thrust than all 4 engines on a Boeing 747 combined. It enables Super Heavy, with 33 engines, to exceed 9,000 tons of total lift-off thrust, more than twice that of the Saturn V. Specific impulse returns to roughly 350 seconds, matching the efficiency of the earliest Raptor designs, while operating at far higher thrust levels. If you've stayed with me all the way to this point, you're already part of a very small group that actually enjoys digging into how these systems work, not just watching the launch footage. If this kind of analysis adds value for you, take a second to hit like, leave a comment, and subscribe to the channel. I focus on the engineering choices behind the headlines and why they matter long before a rocket ever leaves the pad. Your support is what allows these deep dives to keep happening. Engine dry mass drops further to about 1,525 kilograms, compared to Raptor 1's 2,080 kilograms. And total installed mass, including vehicle-side plumbing, shielding, etc., falls dramatically to roughly 1,720 kilograms. For a 33-engine Super Heavy booster, this saves approximately 40 to 43 metric tons of total vehicle mass per launch. It directly translates to more payload, more delta-V, or greater margins. So how can SpaceX do that? This is because the engine's integration burden on the vehicle has been transformed. The propulsion system no longer demands extensive external support structures, shielding, and auxiliary hardware. It arrives as a more complete, self-contained unit. One of the most significant changes lies in how the engine manages heat. Raptor 3 operates without external heat shielding, a choice made possible through fully integrated regenerative cooling across all exposed components. Methane and liquid oxygen flow through internal channels embedded within the combustion chamber, nozzle, and surrounding structures, absorbing heat before combustion and distributing thermal loads evenly. This approach allows the engine to remain naked while maintaining thermal stability during operation. The cooling redesign accompanies a broader evolution in fluid routing. Earlier engines relied on shorter pipes and more complicated welding. Raptor 3 adopts a longer pipe and a much simpler, cleaner weld. Why did they make it longer and simpler? Think of it like this. For a longer pipe, fuel moves through the system with reduced resistance. Pressure losses decrease. Simpler welds allow for faster and more cost-effective manufacturing. The logic mirrors familiar engineering principles outside aerospace. Cable management inside a high-performance computer does not increase raw processing power, yet it improves reliability, cooling, and ease of maintenance while lowering production effort. Raptor 3 applies the same philosophy at a far larger scale. Small changes accumulate into substantial gains when multiplied across hundreds or thousands of engines. Additional mass savings also come from internalizing secondary flow paths and relocating electronics and structural elements within the engine body itself. This approach protects sensitive components while removing the need for external shielding, fire suppression systems, and exposed plumbing. The engine carries less weight, presents fewer failure points, and supports faster turnaround between flights. SpaceX leadership has repeatedly referred to Raptor 3 as a work of art, a phrase that reflects the engine's extreme simplification rather than decorative intent. Visible pipes, flanges, sensors, and auxiliary components have been minimized. Many secondary circuits now exist entirely within the engine structure. Weld joints have been reduced by as much as 75% in certain areas, with bolted flanges replaced by welded connections wherever serviceability trade-offs allow. The overall part count drops accordingly. This simplification directly supports manufacturability. Fewer parts require fewer labor hours, fewer inspections, and fewer opportunities for assembly errors. Production costs have reportedly fallen by a factor of 4 compared to earlier Raptor versions, with further reductions expected as processes mature. Cost efficiency emerges as a consequence of design clarity rather than compromise. Reliability and reuse sit at the center of the Raptor 3 philosophy. The engine is designed for rapid reuse with minimal refurbishment, targeting over 100 flights per unit. Higher chamber pressure capability plays a role here as well. Testing has demonstrated chamber pressures exceeding 330 bar, placing Raptor 3 among the highest pressure operational rocket engines ever developed. Improved turbopump efficiency and refined flow paths support both performance and longevity. By late 2025, Raptor 3 engines had already accumulated thousands of seconds of hot fire testing. That testing provides confidence not only in peak performance, but in sustained operation, thermal cycling, and structural durability. SpaceX continues to rely on testing depth rather than theoretical margins to validate its systems. Flight 12 will serve as the first integrated demonstration of this engine in an operational Starship stack. The mission will test not only thrust and efficiency, but also engine-out behavior, thermal management during ascent, and integration with Starship version 3's evolving structure. SpaceX approaches these flights with the understanding that data matters more than perfection. Raptor 3 represents more than a performance upgrade. It reflects SpaceX's confidence that Starship has moved beyond prototype status. The engine is built for repetition, for manufacturing scale, and for operational cadence measured in routine rather than rarity. Its transformation from the cluttered industrial appearance of earlier Raptors into a clean, sculptural form mirrors SpaceX's broader pursuit of making large-scale spaceflight sustainable through aggressive simplification. The reveal of Raptor 3 ahead of Flight 12 signals that SpaceX is no longer tuning Starship to fly occasionally. It is tuning it to fly often. On January 13th, Elon Musk shared a post comparing Starship to every rocket ever built, summing it up with a simple line: "Starship is the biggest flying object ever made." It wasn't a surprise, but it was a reminder of just how far SpaceX is pushing the boundary. That statement isn't really about size. It's about whether something this large can function as a real transportation system rather than a one-off demonstration. This is where the evolution of Raptor 3 becomes central to the story. The engine isn't designed to make Starship look more impressive on paper. It exists to make a vehicle of this scale operate reliably, fly repeatedly, and do so without turning each launch into a custom engineering project. Raptor 3 increases thrust per engine while reducing the mass and complexity each unit adds to the vehicle. Higher thrust within the existing 33-engine layout improves Super Heavy's liftoff margins without introducing the integration risks that come with adding more engines. At the same time, the substantial reduction in installed engine mass propagates upward through the entire stack. Less weight at the base reduces structural reinforcement requirements, improves center of mass behavior, and directly increases payload capability. On a vehicle as large as Starship, these system-level effects matter more than incremental performance gains.